This video is about a type of thyristor, TRIAC. TRIAC means triode for alternating current. From the name itself we can see it is used for switching the alternating current. The thyristors that we have discussed in the previous videos, that is SCR and UJT, can also be used for switching the alternating current, but the problem is they will switch only the positive half cycle of the AC waveform. They won't switch the negative half cycle of the AC waveform. And even their applications are also different. Majorly, UJT is used to generate a trigger pulse for other devices, and SCR is used to handle the large load applications because the large load applications need continuous current. SCR provides this current even after the trigger is removed. So SCR and UJT applications are different. So TRIAC provides an application where we can switch the alternating current, which is not possible with the UJT and SCR. Now look at the figure. This is the symbol of the TRIAC. It is a 3-terminal device, and we are saying it switches the alternating current, which means it conducts in both the directions. That is why it is a bidirectional switch and a 3-terminal device. You can observe the 3 terminals are gate and main terminal 1 and main terminal 2. Usually in other thyristors, we must have seen that the main terminal 1 and main terminal 2 will be anode and cathode because they are unidirectional devices. But TRIAC is bidirectional, so it does not matter even if the terminals are swapped. So that is why the names main terminal 1 and main terminal 2 are given. And note that the TRIAC represents two thyristors, that is two SCRs connected in anti-parallel having a common gate. The figure here shows the construction of TRIAC. You can observe MT2 electrode is connected to P1 region, MT1 electrode is connected to N2 region, and gate electrode is connected to P2 region. But you have to understand that TRIAC is a combination of two anti-parallel SCRs, right? So, the main terminals MT1 and MT2 electrodes will be connected with both P and N regions of both SCRs. Then only the current conduction can happen in both the directions. And also understand that gate electrode will also be connected with both P and N regions. Then only TRIAC can be triggered by both positive as well as negative gate currents. So remember that TRIAC is a 4-layer device with 6 doping regions. Now let us understand the working of TRIAC when gate is open. When MT2 is positive with respect to MT1 but the voltage is less than forward breakover voltage, then the device does not conduct. This region of non-conduction when MT2 is positive with respect to MT1 is called the forward blocking region. Here the breakover voltage or breakdown voltage means the voltage at which the state of conduction of the device will be such that the device conducts even if this voltage is removed. So, in order to conduct the TRIAC, the voltage should be increased beyond the breakover voltage. Similar is the case when MT2 is negative with respect to MT1. The region in which the device does not conduct if the voltage is less than the breakover voltage is called the reverse blocking region in this case. So, TRIAC conducts in reverse direction only if this voltage is increased beyond the breakover voltage. If we just depend on MT1 and MT2 to make the device conduct, the switching action doesn't occur properly, which means switching action for full positive cycle and full negative cycle will not happen. For proper switching action, proper biasing should be done at the 3 PN junctions of this device. That is why gate terminal is used for reliable triggering and conduction of the device. With gate current, a very small amount of voltage is enough to turn on the TRIAC. So now, let us look at the operation of the TRIAC with the gate pulse applied. Gate voltage can be positive or negative. So, four modes of operation is possible. The figure shows the first mode of operation, that is MT2 is positive with respect to MT1 with a gate polarity positive with respect to MT1. Here MT1 is taken as the reference. When MT2 is positive, the junction between the layers P1N1 and P2N2 are forward biased, whereas the junction between the layers N1 and P2 is reverse biased. With the positive gate signal, holes will be supplied to the P2 region. Now, the reverse bias at P2N1 junction will decrease because of the electrical imbalance that is created due to the positive gate. So now P2 has become more positive than N1, decreasing the reverse bias. So now the TRIAC will conduct and the current will be flowing in the path of P1N1, P2N2. The second mode of operation is when MT2 is positive with respect to MT1 with a gate polarity negative with respect to MT1. Here also the junctions P1N1 and P2N2 are forward biased and P2N1 is reverse biased. The negative signal at the gate pushes the electrons into the P2 region. So now P2 has become more negative, creating the electric field. In TRIAC, the all regions are very closer such that the electric field created due to the negative gate dominates the electric field that is already present due to the reverse bias at the P2N1 junction. So, electrons from P2 region are pushed towards the P2N1 junction. This causes the width of the depletion region to decrease, thereby decreasing the reverse bias at the P2N1 junction. The path of the current flow in this mode is still the same, that is P1N1 P2N2. So now the device will conduct in this mode. The third mode of operation is when MT2 is negative with respect to MT1 with a gate polarity positive with respect to MT1. In this mode, the junctions P1N1 and P2N2 are reverse biased and the junction P2N1 is forward biased. The positive gate injects holes into the P2 region, thereby making P2 more positive with respect to N2. So, the reverse bias at P2N2 junction decreases and it becomes forward bias. So the device conducts and the path for current flow is P2, N1, P1 and 3. And the last mode of operation is when MT2 is negative with respect to MT1 with a gate polarity negative with respect to MT1. Here also the junctions P1, N1 and P2, N2 are reverse biased and the junction P2, N1 is forward biased. The negative gate voltage makes P2 more negative, so the junction P2N2 remains reverse biased, but N4 is more negative compared to P2, so the junction P2N4 becomes forward biased and the electrons from N4 reach P2N1 junction, and since P2N1 junction is forward biased, width of the depletion region is very small, so the electrons reaches N1 and then obviously N1 becomes more negative comparable to P1 and so the width of the depletion region due to reverse bias gets decreased and the device now conducts and the current path is P2 N1 P1 N3. Note that the triggering of mode 1 is more sensitive among all the modes because in mode 1 a smaller gate signal makes the TRIAC on. Now, let us put this entire operation onto a graph and draw the VI characteristics of TRIAC. In the characteristics, you can observe until the breakover voltage, the device is in the off state, but a small leakage current, which is shown in the characteristics, flows because of the reverse bias when the device is in the off state. Once the voltage crosses the breakover voltage, the device conducts and the current increases. Now because the device has become on, if you remove the gate pulse, the device goes to the off state. So the gate signal should be applied until the current reaches the holding current value. Holding current IH is the minimum current required to keep the TRIAC in the on state. Now after current reaches the value of IH, now the trigger can be removed, and even after removing the trigger, the device remains in the on state. The symmetrical characteristics are represented in the fourth quadrant when MT2 is negative. So in this way, a TRIAC switches an AC waveform. This concludes the topic of TRIAC. If you like the video, subscribe to my channel, like and share the video. Kindly help me to help you.